Students, welcome to this lecture. Today's topic is 3D transformation. Now, up till now, we were dealing with 2D transformation. In 2D transformation, there are only two axes, that is x-axis and y-axis, and the objects that we were dealing with were two-dimensional objects such as triangle, rectangle, line, etc., etc. But in 3D transformation, there is one more axis, that is z-axis is introduced. Okay. So this is a z-axis. So x-axis, y-axis, and z-axis. Okay. And we were dealing with three-dimensional objects such as cube or some prisms, pyramids, etc., etc. Okay. So, in three-dimensional transformation, we'll be seeing how to apply different transformations on three-dimensional objects such as cube, pyramids, prisms, etc., etc. Okay. Now, first we'll see how a point is represented in 3D transformation. Okay. So, consider this is a point which is having coordinate x, y, z. Then in homogeneous coordinate system, this point P is represented as x, y, z, h. Okay, where x is a x coordinate, y is a y coordinate, z is a z coordinate, and h is a homogeneous factor, that is 1. Okay, so if a point P is 2, 3, 4, then it will be represented as 2, 3, 4, 1. Okay, so this 2 is x coordinate, 3 is y coordinate, 4 is z coordinate, and h is a homogeneous factor which always be 1. Okay, now we'll see the basic transformations involved in three-dimensional transformations. So we know that there are three basic transformations: translation, scaling, and rotation. So first we start with translation. So transformation now in 2D, the translation transformation is given by 1 0 0 0 1 0 tx ty 1. But in 3D transformation, where one more axis is being added, so we add one more row and one more column to this translation transformation matrix. Now we know that all the transformation matrices, whether it's a 3D or a 2D transformation, they are square matrix. So all transformation in 2D transformation were 3 by 3 size, and all the transformation matrix in 3D will be of 4 by 4 size. Okay, will be of 4 by 4 size. So the translation matrix in 3D is represented as 1 0 0 0 0 1 0 0 0 0 1 0 tx ty tz and 1. Okay, so tx is translation factor along x direction, ty is translation factor along y direction, and tz is translation factor along z direction. Okay, so very simple. If you are knowing 2D transformation well, then it is easy to understand 3D transformation. Now second we'll see scaling transformation. Okay, so scaling transformation about origin. Scaling transformation about origin. So scaling transformation is given by, here the size is 4 by 4. So scaling transformation is given by Sx 0 0 0 0 Sy 0 0 0 0 Sz 0 0 0 0 1. Okay. So this is scaling transformation where Sx is scaling factor along x direction, scaling factor along y direction, scaling factor along z direction. Okay, and the size of this matrix is 4 by 4. Okay. Now the third type of transformation is rotation transformation. Now rotation transformation is very important in 3D. So when you see two-dimensional drawing of an object, front view, top view, side view, then sometimes it becomes very difficult to imagine the actual geometry of an object, okay, actual shape of an object. But if you see the 3D model or isometric model is a 3D model. So if you see the object in isometric model, then it becomes very easy to imagine the actual shape of an object. In 3D rotation, by using 3D rotation, we can actually rotate the object to see the backside of an object. So what features are lied behind the isometric view. Okay, even in isometric view you can see only the two sides. Okay, but if you rotate a 3D object, then you can actually see the features which are not visible from the front side. Okay, so that is why 3D rotation is very important feature or very important transformation, because if you rotate the object, then you can have a complete view of the entire object, and then it becomes very easy to visualize an object. Okay. So next is rotation. Rotation transformation. Okay. Now in 2D we were rotating the object in xy plane. This is xy plane. Okay, this is xy plane. But and to rotate an object, we require point of rotation. Okay, point of rotation. in 2D transform, consider that there is no z axis and we are in 2D transformation. So in 2D transformation, the entire rotation it was happening in xy plane, and to execute rotation we need point of rotation. So point of rotation can be origin, can be any arbitrary point, okay, but the entire rotation is happening in this xy plane, only, okay. So what is the difference between rotation in 2D transformation and rotation in 3D transformation? In 2D transformation, rotation is happening about a point, whereas in 3D transformation, rotation is happening about an axis or about a line, okay. So that is the basic difference between rotation in 2D transformation and rotation in 3D transformation, okay. Now in 3D transformation, this is x-axis, this is y-axis, this is z-axis, okay. So in 3D transformation, rotation is happening about a line or about an axis, okay. So first we'll see the rotation about the three principal axes, that is rotation about x-axis, rotation about y-axis, and rotation about z-axis. So there are three principal axes in 3D transformation. So first we'll see rotation about x-axis. This is rotation about x-axis. This is rotation about y-axis, and this is rotation about z-axis, okay. Now in rotation, the direction of rotation is also very important, okay. For example, we are rotating an object. Consider this is an object, okay, and we are rotating it about x-axis in this direction. Now what is the direction of rotation, whether it's a clockwise or anti-clockwise? Now here we follow right hand coordinate system. We follow right hand coordinate system. Now what is this right hand coordinate system? So we decide the direction always decide the direction by looking along the axis towards the origin, okay. The right hand coordinate system tells us always look along the axis to the origin, okay. Always look along the axis towards origin, okay. So if you see this object is rotating in anti-clockwise, okay, because if you don't follow right hand coordinate system, then if you see this object, then you will see that this object is rotating in anti-clockwise direction, and if you see from the rear view, it looks like it is rotating in clockwise direction, Okay, so a lot of confusion may get arise. So that is why we always follow a right hand coordinate system, which tells us always look the object along the axis towards the origin. So if you are looking along x-axis, then always look in this direction. If you are looking a rotation about y-axis, then always look in this direction, okay, along y-axis towards the origin. And if you are rotating an object about z-axis, then always look in this direction, okay, towards the origin. Now there are three rotations. So first we'll see rotation transformation about x-axis. So rotation transformation about x-axis. So what is the rotation transformation matrix about an x-axis? So Rx, for rotation we use R, and the suffix x represents the rotation is happening about x-axis. Rotate, object is rotating about x-axis. Okay. Now we know that the size of 3D transformation matrix is always 4 by 4, right? It is always 4 by 4, where first column represents x coordinate, second column represents y coordinate, third column represents z coordinate, and fourth column represents the homogeneous factor. Okay, so if you rotate the object about x-axis, then in which plane this object is rotating? The object is rotating in YZ plane. Okay. In which plane this object is rotating? This object is rotating in this YZ plane. Okay. See, this object, if this object is rotating about x-axis, that means this object is rotating in YZ plane. YZ plane. Okay. So since rotation about x-axis, the object is rotating in YZ plane, that is why we keep the cos theta sin theta values at y and z places. Okay. So this is x, this is y, this is z, and this is h. So the rotation about x-axis looks like it is 1 0 0 0 0 cos theta sin theta 0 0 minus sin theta cos theta 0 0 0 0 1. Okay, so rotation about x-axis means the object is rotating in YZ plane. That is why we kept the cos theta sin theta functions at y and z places. Okay, so this is rotation matrix about x-axis. 1 0 0 0 0 cos theta sin theta 0 0 minus sin theta cos theta 0 0 0 0 1, where theta is positive when it is rotating in anti-clockwise direction, looking along the x-axis towards the origin. Clear? Now next rotation is rotation about y-axis. Okay, rotation about y-axis. X, y, z, h, x, y, z, h. So second is rotation about y-axis. So if you rotate an object about y-axis, that means actually we are rotating in xz plane. We are rotating in xz plane. So rotation about y-axis means we are rotating it in xz plane. Okay. So we keep the cos theta sin theta values at x and z positions. So how this rotation about y-axis matrix actually looks like? So it will be cos theta 0, sin theta 0. Now there is no cos theta sin theta values in y positions. So it will be 0, 1, 0, 0. Then in z places, so minus sin theta 0, cos theta 0, 0, 0, 0. Okay. So here rotation about y-axis means rotation is actually happening about xz plane, and that is why we have kept the cos theta sin theta functions at x and z places. Okay. So this is rotation about y-axis matrix. Next is rotation about z-axis. X, Y, Z, H, X, Y, Z, H. Okay. Now this is z-axis and rotation about z-axis. So rotation about z-axis is actually happening in xy plane. Is actually happening in xy plane. Okay. So that is why, because if you see, if the object is rotating about z-axis, that means it is actually rotating in xy plane. Okay, so that is why xy positions will be occupied by cos theta sin theta function. So we'll write down the rotation about z-axis. So rotation about z-axis matrix is cos theta sin theta 0, 0, minus sin theta cos theta 0, 0, 0, 0, 1, 0 and 0, 0, 0, 1. Okay. So this is rotation about z-axis. So here we have seen the rotation matrix about three principal axes, that is rotation about x-axis, rotation about y-axis and rotation about z-axis. Rotation about x-axis means the rotation is actually happening in yz plane. That is why we have kept the cos theta sin theta functions at y and z positions. Similarly, rotation about y-axis is actually happening in xz plane, and that is why we have kept the cos theta sin theta functions at x and z positions. And rotation about z-axis is actually happening in xy plane, and that is why we have kept cos theta sin theta functions at x and z positions. Okay, so this is the basic transformation matrix in 3D transformation. Okay, that is translation, rotation and scaling. Okay, so hope you understand the basic transformation in 3D transformation. Okay, now we'll solve one problems based on 3D transformation. Okay. So here a problem is given: a homogeneous coordinate 3, 2, 1, 1. So this is the coordinates of original point. So original figure is a point having x coordinate as 3, y coordinate as 2, z coordinate as 1 and this is homogeneous factor 1. Okay, is translated. So first transformation is translation, is translated in the x, y, z directions by -2, -2, -2 respectively. So first the point is translated. Okay, so I'll draw the figure. X axis, y axis, z axis. This is a point P. 3, 2, 1. Okay, this is a point, say P. It is translated by -2 in new position by Tx equal to -2, Ty equal to -2, and Tz equal to -2. Okay, respectively, followed by successive 45-degree rotation about y-axis. Then the point is rotated by angle 45 degree about y-axis. So here direction is not mentioned. Okay, whether it's a clockwise rotation or anti-clockwise rotation. So we consider it as an anti-clockwise direction. Means we consider the angle as positive 45 degree, and then followed by 60-degree rotation about x-axis. Okay, then the object is further rotated by 60 degree above x-axis. So there are three types of transformations are involved. First is translation. It is translated, point is translated by a factor -2, -2, -2 along x, y and z direction. Then it is rotated about y-axis by 45 degree, and then it is rotated about x-axis by 60 degree, and we have to find out the coordinate of the final location of this point. Okay, so first will be translation. So this translation transformation will look, so 1 0 0 0 0 1 0 0 0 0 1 0 and tx, ty, tz 1. Okay, now we put the value of tx, ty, tz here. So this matrix looks like 1 0 0 0 0 1 0 0 0 0 1 0 -2 -2 -2 1. Okay, now second transformation. Second is rotation about y-axis by 45 degree. Okay, so rotation about y, ry. Now what is the rotation about y axis matrix? Rotation is actually happening in xz plane, so we keep the cos theta, cos theta, sin theta values on x and z positions. Okay, so it is cos theta 0, sin theta 0, 0 1 0 0, minus sin theta 0, cos theta 0, 0 0 0 1. Now we put the values here. Theta is equal to 45 degree. So if you put the value here, then cos 45 is 0.707, sin 45 is also 0.707, 0 0 1 0 0, minus 0.707, 0, 0.707, 0, 0, 0, 0, 1. So this is rotation about y-axis. Now third is rotation about x-axis by 60 degree. Okay. So rotation about x-axis is written as 1, 0, 0, 0, 0 cos theta sin theta 0, 0 minus sin theta cos theta 0, 0, 0, 0, 1. So rotation about x-axis means the sin theta cos theta values will be at y and z places. So if you put the theta value as plus 60, then this matrix would look something like this. So 1, 0, 0, 0, 0, 0.5, cos 60 is 0.5, 0.866, 0, 0 minus 0.866, 0.5, 0, 0, 0, 0, 1. Okay. Now we are ready with all the three transformations. Now we find out the total transformation by multiplying all the three transformation in correct sequence. So total transformation matrix is equal to, first is translation, second is rotation about y-axis, and third is rotation about x-axis. So if you multiply these three matrices together, you will get the total transformation matrix as 0.707, 0, 0.707, 0, 0, 1, 0, 0, minus 0.707, 0, 0.707, 0, 0, 1.44, minus 3.131. Okay. So this is the total transformation matrix. Now to obtain the final position of this original point, we know that P dash is equal to P into ET. So P dash is equal to, the original coordinate of point is 3, 2, 1, 1 multiplied by the total transformation matrix, this matrix. So you will get the final position of the point as 1.41, 3.44, minus 1.01 and 1. Okay, so this is x coordinate, this is y coordinate, this is z coordinate, and this is homogeneous factor 1. Okay. So this is how we can use 3D transformations for performing various transformations in 3D. Okay. So hope you understand this. So thank you.